So today we're very happy to have Bar-Natan from Toronto, who's gonna tell us about computing the Zombian of an unfinished Columbarium.
I admit everything. Oh, it's jumping. It's keeping. Sorry, the remote does double click instead of single clicks. Yeah, it's skipping one slide every time. Yeah, it goes on the odd slides. This is okay.
What if you do?
Yeah, I'll have to use the keyboard. Sorry. Okay. I wonder if I can pull it. Well, okay. Anyway, sorry about that. So, yeah. What? Sorry, there is some unclear technical issue. And it's hidden by this. Okay, sorry. So yeah, computing the Zombians of unfinished Columbarium is about 50% of what I do. You should know that. I thank you for inviting me to Ottawa. I should also thank some granting agencies, the NSERC and the True Family Foundation. You should all be holding a copy of the handout. I hope you all do. Omega Epsilon Beta stands for this URL. I will refer to it during the talk a number of times. The handout is there. There will be a video later. And maybe I should start by defining the concepts. So a Zombian should rhyme with, well, is something that people like me might want to compute, and it kind of rhymes with Hessian, Wronskian, Lagrangian, Zombian, something that you want to compute, some interesting quantity. A Columbarium is something that you usually find in a cemetery, so it's kind of a big structure with lots of cavities, and in each cavity you put a jar, an urn, with the ashes of the dead. And so a Zombian is something that you compute that pertains to a Columbarium, right? A function value, whose domain is Columbarium. And an unfinished Columbarium is a Columbarium that's not fully specified, so perhaps some of the cavities are still, don't have names on them, are still empty, okay? And the question is, you want to, the zombies sitting there today want to compute as much as possible so that when the future, when the Columbarium will be finished, you will be able to complete the computation as efficiently as possible. So you want to pre-compute as much as you can of the Zombian so that you can finish it at the end. Again, that's about half of what I do in half of what I've been doing in my mathematical career. So, but I also want to give some constraints. So first of all, of course, the future zombies, whatever you compute now, the future zombies should be able to complete the computation when the information will be completed. Second, whatever you do, whatever you do for unfinished Columbaria should not be, at least not much slower than what you would be doing for a complete Columbarium. Otherwise, what's the point? You'll just wait until the Columbarium is finished. And second, so I'm actually thinking of it as a gradual process. So here's the Columbarium, here are the zombies sitting and computing, and here is the rest that's not yet fully specified. And I want the future zombies, so I want what we are computing now. So I want the future zombies to not even know how big the task was before us, before that. So, like, And the reason is, you'll see it later, often the Zombians I care about look a little bit like towers. So they are tall but thin, relatively speaking. And then I want the information that gets passed on to be proportional to the width and not to the height. And that will allow me significant computational savings. And there is an additional an additional condition, but it's grayed out because it's a 20-minute talk. Here are a few exercises. Suppose I wanted to compute just the sum of the entries, the sum of the pieces of information that's in the cavities. So compute the sum of 1,000 numbers, the last 50 of which are unknown. What would you do? What information would you pass to future generations?
Just the sum of the 950.
Good. Satisfies the conditions. Easy to compute and independent, right? It's the sum of the 950. It doesn't matter that there were 950 numbers before. Okay, we've passed just a tiny amount of information. Here's a harder exercise. So you have a 1,000 by 1,000 matrix. So big matrix. But 50 entries in it are still unknown. The Zombian is the determinant. What do you do? So 50 entries are still unknown. What do you do?
Just let them be variables.
Okay, so I'll let them be variables. So I'll put x1 here, x2 here, up to, keep going up to x50. Compute the determinant over a ring of polynomials. The result will be a polynomial in 50 variables of degree about 50. That's a humongous space. It's huge. It's completely dense. So it's a lovely idea, thank you, but it wouldn't work. Maya, please take a copy of the handout over there. Okay? So what do you do? So here's one thing you could do. So you could do it, it was on your handout, you could always read it. So first of all, you do row and column operations to bring all the unknown quantities to the bottom right. Okay, so now I have and this is not necessary, it's only for convenience, it's just for drawing things more. So now the matrix looks like this. It's a big matrix, 1,000 by 1,000, and then the bottom 50 by 50 corner is not known. And in fact, I'm solving a harder problem because this corner may have 2,500 entries, but in particular it has the 50 entries I didn't know about before. Okay? And then, so this is the matrix. It looks like A, B, C, U, where A is huge, B is half huge, C is half huge, and U is small, but U is unknown. Okay? So I do row operations to the top part so as to make this part look like the identity matrix. Really, this means that I multiply on the left by A inverse, the top row. Okay, so I get the identity here, A inverse times B here. And when you compute determinants using Gaussian elimination, if you multiply a row by 7, you have to divide the end result by 7. So now I multiplied by A inverse, so I will have to multiply the end result by the determinant of A at the end. So I get here. Then I do row operations to use this identity here to kill C. So really I'm multiplying the top row, the top block row, by C inverse and subtracting it from the by C and subtracting it from the second row. So this gets killed and the U gets replaced by U minus C A inverse B. And this, adding one row to another, has determinant 1, so the cost is 1, or the way it changes the end result is, it doesn't. And now I got a triangular matrix whose determinant is the determinant of this block multiplied by the determinant of that block. So overall, I'm finding that the determinant of ABCU is the determinant of A times the determinant of U minus CA inverse B. So the information I'm passing on to future zombies will be the determinant of A, a single number, and negative C times A inverse B, and that's a 50 by 50 matrix. So that's small. I'm passing on an information, that's amount of information that was independent of the 950. Okay? And then the future zombies who need to compute complete the computation will take U, the unknown piece, add to it what I've passed on, compute the determinant, multiply by the determinant of A, and they're done. Okay, so that's easy enough. Yes?
I think I don't understand why a 50 by 50 matrix is less information to pass on than a degree 50 polynomial.
Degree 50 polynomial with 50 variables, or in fact,
I mean,
really,
it's 50 coefficients compared to like 50 times.
no,
50,
it's not
right?
50 coefficients. A polynomial with 50
Oh,
unknowns.
I see. Okay, yeah, great. Yeah.
It's actually 2 to the 50 coefficients.
Sure. Yeah, great.
Okay?
Yeah, thank you.
And by the way, you can think of it as if there is a projection map here. So the projection map is basically it projects the information below the computation line to the computation line. And I kind of want to forget to evaluate everything in the kernel of this projection. Okay, I want to figure out what to do with everything in the kernel of this projection. And with this kind of very rough view, the determinant on the kernel is, the determinant of A is roughly the determinant of on the kernel. And you can think of negative CA inverse B as some sort of a push forward to the boundary, to the unknown world of the matrix ABCU. And I'm using this language because it will be a bit more relevant in the next example. So exercise for you, what do you do if A inverse does not exist? Okay? But having said this, let's move on to the next example. So the next example is do exactly the same, but instead of the determinant, compute the signature. So now the Zombian is the signature of a matrix, and the matrix is really representing a quadratic form, so it's a symmetric matrix over the reals or a Hermitian matrix over the complex numbers. Okay, so the signature of a matrix, maybe I should have said that. So, maybe I'll skip the abstractness, but a quadratic form is a certain function given by a quadratic formula. A quadratic formula is something of the form sum of aij eta I eta conjugate eta j, where A is a Hermitian matrix. And the signature is, so you use row and column operations, but the same row and column operations, to bring the matrix to as close as you can to a diagonal form. You can bring it to the form only ones and minus ones on the diagonal and zeros, and then the signature is the number of ones minus the number of zeros. Okay? So how do you compute the signature of a partially given quadratic? So I actually need a new, so I should say what I'm going to say now is joint work with my student Jessica Liu, who is amazing, and sooner or later you'll hear more from her. And I should also define a new notion. So a partial quadratic is a quadratic defined on a subspace called the domain of the partial quadratic, a subspace of the overall space. When you add partial quadratics, you intersect the domains. And I should say that given a map between vector spaces, there is an obvious pullback map if you have a quadratic function on W, obviously you can compose it with psi, and you get a quadratic function on V. So there is an obvious pullback map, and then our theorem says that given a linear map phi from one vector space W, V, to another double vector space W, and given a partial quadratic on the domain vector space, there is a push forward to the target vector space, and it's a unique partial quadratic defined on the target vector space that has the property that whenever you have a partial quadratic U on the target vector space, so you should be thinking of Q as the known quadratic and U as the unknown part, and it's defined on the relatively small target of the forgetful map, which forgets everything that we know except the boundary. And then for every such U, the following property holds. So the signature of the original quadratic plus the unknown. So basically the signature of the original thing plus the new stuff, the unknown stuff pulled to the big space, is equal to the signature of the original quadratic reduced to the kernel of the projection. It's not a projection, it's a general linear map to the kernel of phi, plus the signature of the unknown. So this is the signature computed on the target space, which is presumably a small space, of the unknown quadratic plus the push forward of the original quadratic. The push forward is something that lives on a small space. So this theorem solves the problem for signatures. Now, I think I have 20 minutes and 16 of them are gone, so I will not show you the proof, but the proof is basically matrix manipulation and then interpreting what you see. But you can read more about, you can learn more about it by going to omega epsilon beta / iserm, where there is a video of a talk in which this was done in more detail. And now a word about knots and tangles, and I really have to go quickly, I'm sorry about that. So here are knots. Here are also knots. So this is one of the standard nautical knots tables. And if you look at it more carefully, you'll see that what people in the boating business call knots, like a reef knot or a granny knot, is actually what we would call a tangle. For some reason, we as mathematicians don't care as much about tangles as we should, but we should. So one reason is that they are as common as knots. Another reason, well, we've just seen that. Real people think of think of tangles as knots. Another reason is that they lead to faster computations. Exactly if, so you think of a tangle as being an unfinished knot or a part of a knot, and then if you're able to extend your Zombians to unfinished knots, so to tangles, then, for example, if you want to compute the Kaufman bracket, so the Kaufman bracket is usually computed by replacing a crossing by a 0 smoothing plus a 1 smoothing, and that's a 2 to the n, complexity 2 to the n computation, because you have to do it to n crossings. But if you know how to do it to tangle, you cut the tangle into a half, the knot into a half. You do a computation on the left and a computation on the right. Each one takes 2 to the n over 2. Then you have to pay some price for the gluing, and typically you can cut so that the size where you need to glue is square root of n, so that the boundary is of length of size square root of n, and then you have to pay an extra fee of 2 to the square root of n, but that's still a lot less than 2 to the n. So you gain a lot once you know how to extend your Zombian to unfinished Columbarium. You get conceptually clearer proofs of invariance because basically the Reidemeister moves are equalities between tangles. And and the main reason is that often it is fun and consequential. So if you try to do it to the Alexander polynomial, you end up, Alexander polynomial is the determinant, you end up thinking about you take the Zombians to be the determinant, and that's exactly one of the stories I told you. If you want to compute knot signatures, we heard about them yesterday, then you end up studying the push forwards of quadratic forms, which is a fun thing, and I just told you about it a little more. The Jones polynomial leads you to think about the temporally Lieb algebra. Chovanov homology leads you to think about how do you compute the homology of a complex which is not in which the maps are not yet specified. You end up thinking about complexes in a category, modulo homotopy, blah blah blah. And I mean, I told you that's about half of what I do. And if you want to think about the Kontsievich integral, whatever that might be, you end up learning about Greenfield associators and the like. Do I have another minute?
Yes, please go ahead.
Okay, sorry. So I wanted to just mention one dream that I have. I can't do it. I don't know how to do it, but I just wanted to tell you about my dream. So my dream is about knot tabulation. So first of all, knot tabulation has a huge history. Here it is, okay? And then it continues, like this I stole from Jason Parsley with permission, and you can see the original over here, but the history continues after Parsley wrote his slides. So there is a tabulation by Burton to 19 crossings, and on my influence, a student of mine redid the Rolfson table up to, which is just the first 250 knots, and you can read about it here, and the point is that it was supposed to become simpler. And now I have to make to acknowledge two embarrassments. The first one is personal. You know, as a mathematician, I kind of believe that you should not use what you cannot prove. In fact, even like the software that runs the presentation right now, I wrote myself. I tend to be self-contained, okay? But it's a huge personal embarrassment to admit that the Rolfson table, which I use every day, every time I test whatever Zombian is on my mind on that day, I use the Rolfson table and I cannot reproduce it myself. It's a true embarrassment. Now, yes, I could farm it out to a student and then he did it, but he did it, I didn't. He took a summer to do it. I want to be so good that I would be able to do it in an afternoon, a day, fine. Take a week, okay? And it's harder than it seems because producing all knot diagrams is a mess. Identifying all the Reidemeister moves is a mess. And when I say it's a mess, I also mean a very large space in which to work. And sometimes two knots are equal, but to get from one to the other, you have to go up in complexity before you can go down again. So you actually so you have to go into bigger messes, even if you just want to reproduce the Rolfson table. So this is my personal embarrassment, and then there is a communal embarrassment. All of us should be embarrassed. There isn't a tabulation of tangles. There isn't a good tabulation of tangles. When you want to test your new half-Zombians, what do? Okay? So my dream is to conquer both embarrassment at once, one day. So one day to figure out, to learn, and I still don't know how to do it. It's a dream. I keep thinking about it. I have ideas, but I don't have results. So I want to be able to reproduce the Rolfson table and extend it to tangles using code that would be so beautiful and so meaningful and so easy that you will be able to do it in one day, maybe one afternoon, without any technicalities. It should just be beautiful, okay? And there is a chance. And the chance is because of the following reasons. First of all, once you think about tangles, so suppose you've done a simplifying Reidemeister move on the tangle, on the half knot on the left. From that, when it was still a tangle. From that point on, you never need to look at this anymore. You only need to look at that. So in principle, you don't even need to enumerate all knot diagrams, because some of them are simplified already at the stage where it's a tangle. Second, the dreaded slide moves. So these are the moves that go up in complexity and down, and then down again. They're basically parameterized by tangles. So if your program parameterizes tangles along parameterizing knots, you have a go, you have a chance. And finally, the Reidemeister moves themselves are tangle equalities, so you don't even need to implement them. You just need to know, you just need to talk about tangles and modding out by tangle equalities such as this and that. So there is a chance, I still don't know how to do it, and I'm 5 minutes and 40 seconds over time.
Minus technical issues.
Thank you for listening. I know you'll program it in 5 minutes, but
No,
I will not, so the embarrassment will remain mine, even if it's not yours. Yes?
Yeah, no. Sorry, can you please say again, what do you mean we don't need, in the left lower corner, we don't even need to look at all knot diagrams?
Yes.
I'm sorry, could you say again?
So,
What do you
so
want?
suppose I have a big knot,
Yeah.
and I cut it in half, okay? And I study tangles along with studying knot, and in particular, each half is a smaller tangle, so I've already studied it. Okay? So, on the tangle on the left, you know, really there are lots and lots of tangle diagrams, and I will have to look at all of them, but many of them I will cross out as irrelevant because they are equivalent by Reidemeister moves to simpler ones, or to ones that are lexicographically earlier.
Yeah, so,
Okay.
so what you mean is you want a minimal table of tangles.
Yes.
Like Robson table for tangles.
Yes, and I'm saying that if I produce it along with the production of knots, it will simplify the production of knots. And in fact, how would you produce tangles? You'd cut them in half and produce each half and then learn how to assemble. So yes, so that's what I don't know how to do.
Can I ask, so at least for the part about knots, this looks something like kind of a TQFT or categorified structure, except it doesn't really have a linear space as its target. But is this a helpful way of thinking at all?
You mean, is it
Like this picture in the upper right, like it's kind of a TQFT picture.
Maybe I should have added here that TQFTs, the whole subject of TQFTs, are an example of computing the Zombian of an unfinished Columbarium, right? You want to compute the partition function, and the TQFT philosophy tells you cut the manifold in half, compute something more complicated for the left half than for the right half, and then figure out how to assemble. So yes, TQFT
kind of
is an example.
Like classifying tangles on the other side.
Yeah, but it goes beyond TQFT. So I don't know if like what I told you about signatures can be thought of usefully as a TQFT story. But now I think about it, and I know my advisor, and had he been here, he would have laughed at me and said, "Of course it's a TQFT." I mean, for some people, everything is a quantum field theory story.
I guess
so.
I just mean like if you're thinking about tangles as columns between collections of points.
Yeah.
then like this gets some sort of categorical structure, right? Where like a knot is a Hom from the empty set to the empty set, and then you can kind of factor in the intermediate Homs. I mean, none of this has any linear structure, but so I don't know. It might be something you notice, and it's completely not useful
I don't
at
know
all.
what to
or,
say.
like,
I don't know what to say. I'm not sure what to say.
okay.
I mean, obviously, all of these stories, I just given you the tip of the iceberg. Like, all of these stories are huge, and I've just told you a minute about each one. I mean, even the simplest one, the Alexander polynomial, is a huge story. Yeah.
Whenever you tabulate knots, it's usually like prime knots, right? How simple or would you want the tangles to be? Because like you can like stack them, you can compose them.
I think, well, okay, I mean, I don't know how to do tangles, right? But I think the answer is you want to tabulate non-prime knots and non-prime tangles. I mean, you want to tabulate everything, and then it's relatively easy to find the prime ones within them.
Oh, okay.
Because you just multiply what you've tabulated on the previous days, the lower complexity things. So you just, I think the right thing is to just tabulate everything, and then at the level where you show off to others, you remove, you cancel out the things that you don't want to show.
But maybe the code would like save time by
If the
knowing
code,
that
maybe I should have added it as another part of the dream, right? But the moment tangles are in, I also want tangle multiplication to be in. And then the moment tangle multiplication is in, identifying non-prime things is completely obvious. It was completely easy.
Are there any other questions? If not, let's thank Drew again.